To achieve safe, effective, quick, and code-correct wiring for a power unit test station, consider these options. Firstly, install a safety interlocked receptacle with a removable power cord connector on the motor control center, or MCC. Wire the power cord directly to the power unit motor and connect it to the receptacle when testing. The interlock prevents energizing the circuit when the receptacle is open, ensuring operator safety. Secondly, mount a disconnect switch with an industrial-grade plug and socket on the MCC. Wire the power cord to the power unit motor and connect it to the socket. When not in use, lock out the disconnect switch for safety. Thirdly, use industrial-grade quick-connect electrical connectors, such as cam lock or power lock, to connect the power cord to the power unit motor. Ensure proper grounding and secure connections for safety and to prevent arcing. In addition to those options, implement these additional safety measures. Ensure the power cord is inspected regularly for damage or wear. Place the test station in a well-ventilated area to prevent overheating. Provide proper signage to alert personnel about testing activities. Train personnel on safe operating procedures. All wiring should comply with the National Electrical Code, or NEC, and local electrical codes. Use proper wire gauge conduits and termination methods. Obtain appropriate permits and inspections as required by local authorities. Let's delve deeper into each of these options, starting with the safety interlocked receptacle. This system provides a robust safety mechanism by preventing the circuit from being energized unless the power cord is properly connected and the interlock is engaged. The receptacle should be heavy-duty and rated for the appropriate voltage and amperage for the power units being tested. The wiring from the MCC to the receptacle should be done using the appropriate gauge wire, run in conduit, and terminated properly in a junction box. The power cord that connects to the power unit motor should also be of appropriate gauge and length. The connector on the end of the power cord should be compatible with the safety interlocked receptacle. When installing this system, ensure that the interlock mechanism functions correctly. Test it to verify that the circuit cannot be energized when the receptacle is open. Label the receptacle clearly to indicate its purpose and voltage. The second option, using a disconnect switch with an industrial-grade plug and socket, provides a readily accessible means of disconnecting power to the power unit. The disconnect switch should be sized appropriately for the motor's horsepower and voltage. The industrial-grade plug and socket provide a secure and reliable connection. Wire the power cord to the power unit motor and connect it to the socket. When not in use, the disconnect switch should be locked out to prevent accidental energization. Mount the disconnect switch in a location that is easily accessible. Wire the disconnect switch to the MCC using the appropriate gauge wire and conduit. The plug and socket should be rated for the voltage and amperage of the power unit. Ensure that the plug and socket are properly grounded. Label the disconnect switch clearly to indicate its purpose and voltage. The third option, using quick connect electrical connectors, offers a fast and efficient way to connect and disconnect power to the power unit motor. These connectors are typically used in heavy industrial applications where frequent connections and disconnections are required. Examples include cam lock or power lock connectors. These connectors are designed to provide secure and reliable connection, even in harsh environments. When using quick connect connectors, it is crucial to ensure proper grounding. The connectors should be rated for the voltage and amperage of the power unit. Use the appropriate tools for installing and removing the connectors. Inspect the connectors regularly for damage or wear. Secure the connections to prevent accidental disconnection. Provide strain relief for the power cord to prevent damage to the connectors. Clearly label each connector to indicate its purpose and voltage. Remember that regardless of which option is chosen, several additional safety measures should be implemented. The power cord should be inspected regularly for any signs of damage or wear. Look for cuts, abrasions, or exposed wires. Replace the power cord immediately if any damage is found. The test station should be located in a well-ventilated area to prevent overheating. Hydraulic power units can generate heat during operation, and adequate ventilation is essential to prevent the risk of fire or equipment failure. Provide proper signage to alert personnel about testing activities. The signage should clearly indicate the potential hazards associated with the test station, such as electrical shock and moving parts. Train all personnel who will be operating or working near the test station on safe operating procedures. The training should cover topics such as lockout-tagout procedures, proper use of personal protective equipment, and emergency shutdown procedures. All wiring must comply with the NEC and local electrical codes. The NEC provides comprehensive guidelines for safe electrical installations. It is essential to consult the NEC to ensure that all wiring is done in accordance with its requirements. Local electrical codes may also have additional requirements that must be met. Use the proper wire gauge for the amperage of the circuit. The NEC specifies the minimum wire gauge that is allowed for different amperage ratings. Using a wire gauge that is too small can result in overheating and fire. Run all wiring in conduit to protect it from physical damage. Conduit is a metal or plastic tube that is used to enclose electrical wiring. It provides protection from moisture, abrasion, and impact. Use proper termination methods to ensure secure and reliable connections. Proper termination methods include using the correct type of connectors and tightening screws to the proper torque. Obtain appropriate permits and inspections as required by local authorities. Most jurisdictions require electrical permits for new installations and modifications to existing electrical systems. An electrical inspection is typically required after the work is completed to ensure that it meets code requirements. Now, let's address some common questions about wiring power unit test stations. What size disconnect switch should I use? The size of the disconnect switch should be based on the motor's horsepower and voltage. Consult the motor's nameplate to determine its horsepower and voltage. Then refer to the NEC to determine the appropriate disconnect switch size. What type of wire should I use? The type of wire should be based on the application and the environment. The NEC specifies different types of wire for different applications. For example, THHM wire is commonly used for general purpose wiring, while XHHW wire is used for wet locations. The wire should also be rated for the voltage and temperature of the application. What type of conduit should I use? The type of conduit should be based on the environment and the type of wiring being used. Rigid metal conduit is the most durable type of conduit and is often used in industrial applications. Electrical metallic tubing, or IMT, is a lighter weight type of conduit that is commonly used in commercial applications. PVC conduit is a non-metallic type of conduit that is resistant to corrosion. How should I ground the test station? The test station should be grounded to provide a path for fault current to flow back to the source. This helps to protect personnel from electrical shock. The grounding conductor should be connected to a grounding electrode, such as a ground rod or a metal water pipe. The size of the grounding conductor should be based on the size of the circuit conductors. How often should I inspect the wiring? The wiring should be inspected regularly for any signs of damage or wear. The frequency of inspection should be based on the environment and the usage of the test station. In harsh environments or where the test station is used frequently, inspection should be performed more often. In addition to the above, let's consider some potential challenges and solutions. Challenge 1: difficulty in accessing the motor control center. Solution: consider using a remote disconnect switch or a portable power distribution unit. Challenge 2: space constraints within the motor control center. Solution: utilize compact disconnect switches and connectors. Challenge 3: ensuring proper grounding in a noisy electrical environment. Solution: employ dedicated grounding conductors and consider using isolated ground receptacles. Challenge 4: preventing accidental restarts during maintenance. Solution: implement a robust lockout-tagout procedure and use safety interlocked devices. To summarize, creating a safe and code-correct wiring system for a power unit test station involves careful planning, proper selection of components, and adherence to all applicable codes and regulations. By implementing the options and safety measures described, it is possible to create a test station that is both efficient and safe for personnel. Remember to consult with a qualified electrician to ensure that all work is performed in accordance with local requirements. Here are some additional points to consider. Documentation: keep detailed records of all wiring and electrical modifications performed on the test station. This documentation should include wiring diagrams, equipment specifications, and inspection reports. Training: provide ongoing training for personnel who operate or maintain the test station. This training should cover topics such as electrical safety, troubleshooting, and maintenance procedures. Regular audits: conduct regular safety audits of the test station to identify potential hazards and ensure that all safety procedures are being followed. Emergency procedures: develop and implement emergency procedures for dealing with electrical accidents, such as shocks and fires. These procedures should be clearly communicated to all personnel. Personal protective equipment: ensure that all personnel who work on or near the test station wear appropriate personal protective equipment, such as safety glasses, gloves, and insulated shoes. Lockout tagout: implement a comprehensive lockout tagout program to prevent accidental energization of the test station during maintenance. This program should include written procedures, training, and lockout devices. Signage use: clear and conspicuous signage to warn personnel of potential electrical hazards. This signage should include warnings about high voltage, shock hazards, and arc flash hazards. Ground fault circuit interrupters, or GFCIs: consider using GFCIs to protect personnel from electrical shock. GFCIs are devices that detect ground faults and quickly interrupt the circuit, preventing serious injury. Arc flash protection: conduct an arc flash hazard assessment to determine the potential arc flash hazards at the test station. Based on the results of the assessment, implement appropriate arc flash protection measures, such as using arc-rated clothing and equipment. Regular maintenance: perform regular maintenance on the test station to ensure that all components are functioning properly. This maintenance should include inspecting wiring, tightening connections, and testing safety devices. Environmental considerations: consider the environmental conditions in which the test station is located. If the test station is located in a damp or corrosive environment, use components that are rated for those conditions. Modifications: ensure that any modifications to the test station are performed by qualified personnel and that all work is done in accordance with applicable codes and regulations. By following these guidelines, it is possible to create and maintain a safe and efficient power unit test station. Remember that electrical safety is paramount, and it is always better to err on the side of caution. When in doubt, consult with a qualified electrician. Let's dive into the specifics of grounding, as it's a crucial aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing a dangerous buildup of voltage. There are several types of grounding systems, including solidly grounded, impedance grounded, and ungrounded systems. The choice of grounding system depends on the specific application and the level of protection required. In most industrial applications, a solidly grounded system is used. In a solidly grounded system, the neutral point of the transformer or generator is directly connected to ground. This provides a lower impedance path for fault current and helps to minimize voltage rise during a fault. The grounding conductor should be sized according to the NEC. The size of the grounding conductor depends on the size of the circuit conductors. The grounding conductor should be made of copper or other conductive material and should be properly insulated. The grounding conductor should be connected to a grounding electrode, such as a ground rod, a metal water pipe, or a ground ring. The grounding electrode should be buried in the ground and should provide a low resistance connection to earth. In addition to the equipment grounding conductor, which connects the non-current carrying metal parts of equipment to ground, there is also a grounding electrode conductor, which connects the grounding electrode to the neutral point of the electrical system. The grounding electrode conductor should also be sized according to the NEC. The grounding electrode conductor should be made of copper or other conductive material and should be properly insulated. Proper grounding is essential for preventing electrical shock and fire. It is important to ensure that all grounding connections are tight and that the grounding system is properly maintained. Regular testing of the grounding system is recommended to ensure that it is functioning properly. Moving on to another important topic, let's discuss overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload is a condition in which the current in a circuit exceeds the rated capacity of the circuit conductors. A short circuit is a condition in which there is a low resistance path between two conductors, resulting in a very high current flow. Overcurrent protection devices are designed to interrupt the flow of current in a circuit when an overload or short circuit occurs. This prevents damage to equipment and reduces the risk of fire. Circuit breakers and fuses are rated in amps. The amp rating indicates the amount of current that the device can carry continuously without tripping or blowing. The amp rating of the overcurrent protection device should be matched to the ampacity of the circuit conductors. The ampacity of a conductor is the maximum amount of current that it can carry safely without overheating. The ampacity of a conductor depends on its size, insulation type, and installation method. The NEC provides tables that list the ampacities of different types of conductors. Circuit breakers are resettable devices that can be tripped manually or automatically. Fuses are one-time devices that must be replaced after they blow. There are different types of circuit breakers and fuses, each designed for specific applications. For example, inverse time circuit breakers are designed to trip faster as the current increases. This type of circuit breaker is commonly used to protect motor circuits. Time delay fuses are designed to withstand temporary overloads without blowing. This type of fuse is commonly used to protect circuits that supply motors or other inductive loads. It is important to select the correct type of overcurrent protection device for the application. The overcurrent protection device should be installed in a readily accessible location. The overcurrent protection device should be labeled to indicate the circuit that it protects. Regular testing of overcurrent protection devices is recommended to ensure that they are functioning properly. Now let's talk about wire selection. The selection of the correct wire for an electrical installation is crucial for safety and reliability. The NEC provides detailed guidelines for wire selection, taking into account factors such as ampacity, voltage rating, insulation type, and environmental conditions. The ampacity of a wire is the maximum amount of current that it can carry safely without overheating. The ampacity of a wire depends on its size, insulation type, and installation method. The NEC provides tables that list the ampacities of different types of wires. The voltage rating of a wire is the maximum voltage that it can safely withstand. The voltage rating of the wire should be equal to or greater than the voltage of the circuit. The insulation type of a wire determines its ability to withstand heat, moisture, and chemicals. The NEC specifies different types of insulation for different applications. For example, THHN wire is commonly used for dry locations, while XHHW wire is used for wet locations. The environmental conditions in which the wire will be installed also affect wire selection. For example, if the wire will be exposed to direct sunlight, a sunlight-resistant wire should be used. If the wire will be exposed to corrosive chemicals, a chemical-resistant wire should be used. The size of the wire should be based on the ampacity of the circuit and the length of the wire run. The longer the wire run, the larger the wire size that is required to prevent voltage drop. Voltage drop is the decrease in voltage that occurs along a wire run due to the resistance of the wire. Excessive voltage drop can cause equipment to malfunction or fail. The NEC provides guidelines for calculating voltage drop. The wire should be installed in accordance with the NEC and local electrical codes. The wire should be properly supported and protected from physical damage. The wire should be terminated properly using the correct type of connectors. Now let's discuss the importance of proper electrical connections. Proper electrical connections are essential for ensuring the safety and reliability of electrical systems. Loose or corroded connections can cause overheating, voltage drop, and even electrical fires. All electrical connections should be made in accordance with the NEC and local electrical codes. The correct type of connector should be used for the application. The connector should be sized appropriately for the wire size. The connector should be properly installed using the correct tools and techniques. All connections should be clean and free of corrosion. Antioxidant paste should be used on aluminum connections to prevent corrosion. Connections should be tightened to the proper torque. Over-tightening can damage the connector or the wire. Under-tightening can result in a loose connection. Regular inspection and maintenance of electrical connections are important to ensure that they remain tight and corrosion-free. Loose or corroded connections should be repaired or replaced immediately. In addition to the above, let's explore the topic of arc flash. Arc flash is a dangerous phenomenon that can occur when there is a short circuit or fault in an electrical system. Arc flash events can generate intense heat, pressure waves, and projectiles, which can cause serious injury or death. An arc flash hazard assessment should be conducted to determine the potential arc flash hazards at the test station. The assessment should take into account factors such as the voltage of the system, the available fault current, and the distance from the equipment. Based on the results of the assessment, appropriate arc flash protection measures should be implemented. These measures may include using arc-rated clothing and equipment, installing arc flash barriers, and implementing safe work practices. Arc-rated clothing and equipment are designed to protect workers from the heat and flames of an arc flash. Arc flash barriers are physical barriers that are designed to protect workers from the projectiles and pressure waves of an arc flash. Safe work practices include energizing equipment before working on it, using insulated tools, and maintaining a safe working distance. Training is essential for workers who may be exposed to arc flash hazards. Workers should be trained on the hazards of arc flash, the proper use of arc flash protection equipment, and safe work practices. Finally, let's discuss the importance of following lockout-tagout procedures. Lockout-tagout, or LOTR, is a safety procedure that is used to prevent accidental energization of equipment during maintenance or repair. LOTR procedures involve isolating the equipment from all energy sources, such as electricity, compressed air, and hydraulic pressure, and then attaching a lock and tag to the energy isolating devices. The lock and tag prevent anyone from accidentally energizing the equipment while it is being worked on. A written LOTR program should be developed and implemented. The program should include procedures for identifying energy sources, isolating equipment, attaching locks and tags, and verifying isolation. Workers should be trained in the LOTR program and procedures. Only authorized workers should be allowed to perform LOTR procedures. Locks and tags should be standardized and easy to identify. Locks and tags should be durable and resistant to tampering. LOTR procedures should be followed every time equipment is being maintained or repaired. Verifying that equipment is properly isolated before starting work is crucial. Regular audits of the LOTR program should be conducted to ensure that it is being followed properly.